Okay, in this lecture we're going to discuss this topic of continuous probability distributions. The way we're going to do that is we're going to present some examples of those. Our first example is that of a uniform probability distribution, then a skewed one, and then a normal distribution. Notice that when we discuss skewed probability distributions, there are two types, right and left. Skewed right and skewed left. So let's proceed. When we talk about continuous probability distributions, our random variable happens to be a continuous random variable. In order to construct pictures of these histograms, probability distribution histograms, we have to talk about these probability functions. So let me quickly say that f is a probability function. If you have a function f, it will be a probability function. It's a probability function if two conditions are satisfied. First condition is that f of x is greater than or equal to 0 for all x. So you cannot have negative values for fx. And the second condition is that the area under the curve, the area under the graph, between the graph and the x-axis is exactly 1. Area under curve is 1. So that's what it takes for a function to be a probability function. So let's look at what a uniform probability distribution will be. So what it is, it's a distribution whose probability function is either 0 or constant. So let me draw a picture of an example. Say this is your data axis, your x-axis, and there is your vertical axis. Let me define an example of a uniform probability distribution. So it's either 0 or a constant greater than 0. So to the left of the vertical axis, I'm going to make it 0. And to the right here, I'm going to make it 0. Now let's say this is a 4 and fx is 1/4. So you have, in this case, that's your function f of x equals to 1/4 for x between 0 and 4, 0 elsewhere. That right there is a uniform probability distribution. Now, does it satisfy the conditions for this to be a continuous probability distribution? Well, let's see. F of x greater than or equal to 0, yes, that graph of f is never below the x-axis. Now, is the area under the curve equal to 1? Well, let's see. Let's do some. If you do some geometry, you'll find out that this is a rectangle, and you know that the area of a rectangle is base times height. So the area under the curve is going to be equal to base times height, which is 4 times a quarter. 4 times a quarter is 1. So there we have it. An example of a uniform continuous probability distribution. Now I'm going to erase here this example, and now let's look at a couple of pictures for skewed distributions. In this second example, I'm not going to show an actual probability function. What I'll show is what the histograms look like. So I don't have right now specific formulas that will exemplify skewed distributions, but I would like to just illustrate what the histograms look like. So something that's skewed right will have the following shape. Here is your probability function. There is the skewedness, skewed right. Now, does it satisfy the conditions for a probability function? This is y equals fx right there. F of x greater than or equal to 0. Yes, the graph is above the x-axis, above the data axis. So far we meet the first condition. Now, to meet the second condition, you have to have a formula for fx that gives you an area under the curve of 1. So let's say that this area equals 1. So for this type of picture, area under the curve equals 1, you have a skewed continuous probability distribution, skewed right probability distribution. Now let's see what one skewed to the left looks like. So again, here is your data axis. So it's kind of the opposite. The skewedness is now left, so it's going to look something like this. Again, let's call this y equals g of x. You have to meet the conditions g of x greater than or equal to 0. Yes, that graph is above the x-axis, so that condition is met. Whatever the formula for g of x would be, you have that it needs to be 1 that gives area under the curve equal to 1. So here are our two examples, picture examples of skewed continuous probability distributions. Now we're going to look at an example of what a normal distribution looks like. It is widely studied in basic statistics course. There is a lot of attention paid to this type of continuous probability distributions, the normal ones. So first let me state that we do have knowledge of what the probability functions look like for normal distributions. So they look something like this: fx equals to some constant e to the negative some other constant x minus h squared. Now the constants here c and d must be greater than 0, and h could be anything. It's like a shifting factor, a shifting constant. Now what the specific constants have to be is known. If you were to study statistics at an advanced level, not necessarily an introductory level, but if you're study statistics at an advanced level, you will actually see that all normal distributions have probability functions that look like this. Let me see if I can point it well. A probability function for a normal distribution with mu in standard deviation sigma has this formula right there: y equals 1 over sigma square root of 2 pi e to the negative 1/2 x minus mu over sigma all squared. So as you can see, c and d do depend on the mean in the standard deviation of the distribution itself. Now here is the interesting fact is that this is a let me show you again. This is a probability function. It does satisfy your two conditions. If you were to graph it, the graph of that function will look something like a bell. It's a bell-shaped curve. So if you graph this, it will look something like that. And with the formula I've shown you, it can be proven that that area under the curve is 1. So there is your normal distribution. Now before I conclude, I will show you that even calculators are capable of analyzing a function like that. I earlier asked my calculator to graph a normal distribution function and calculate the area under the curve. I don't know if you can see it in the screen, but it came up with 0.999999968. Of course, the calculator has some rounding error. It should have been 1. Mathematically, it is a fact that if you look at the graph of your probability function for a normal distribution, when you compute the area under the curve between the x-axis and the curve, you will actually get an area of 1. So there we have our 3 examples, and that is it for now.